Hello, now everybody. I want to start discussing the next section in the Schrodinger's quantum mechanical model of atom, and this one is what we talked about. It's called Pauli Exclusion principle. Pauli Exclusion principle. Let's do a recap as is shown on this picture. This is the pictorial representation of Schrodinger's model, and as you can see, it is there's a nucleus in the middle. It contains the protons and neutrons, and now it has, just very similar to Bohr's model, you have a principal energy level. It's called a principal energy level. It's represented by the N, the quantized representation. N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, N equals 6. It can go on. It can go on forever. And Bohr stopped there. Schrodinger didn't. So now you have a finer details. Now you have the sublevels. We call it S, P, D, and F. In the G, H, I, and it keeps on going. So on the first principal energy level, you have a 1s. On the second principal energy level, you have 2s, 2p, and the third you have 3s, 3p, 3d. Fourth you have 4s, 4p, 4d, 4f, and the 5 you have 5s, 5p, 5d, 5f, and the 5g keeps on going. I put a circle on the 5g's because for the ground state electron configuration, for all the known elements on the periodic table, you do not need the 5g. And on those sublevels S, P, D, F, G, H, I, they are orbitals, and the orbitals, as we said before, three-dimensional regions is probability function. It's 90%. You will find a certain type of electron or electrons on there. So on the S sublevel, you always have one orbital. So you have a 1s, you have one little square that's representing one orbital. 2s, you have a square. Excuse me. 3s, you have a square. 4s, 5s, and 6s all have one squares. Now you go into the P sublevels, and then you have three orbitals for 2p, 3p, 4p, 5p, and you go to the third principal energy level, you have the 3d sublevels. Those have five orbitals. The F sublevels have 7, the G will have 9, the H will have 11. It goes on and on. So that's a little bit recap. Now today we're going to review is, ultimately we want to have those electrons put it on those orbitals. So the question is, for each of those boxes, this is an orbital. This is an orbital. It's how many electrons I can put it in. So to start think about it, electrons, it's a little dot, tiny dot, and it carries a charge. It's a tiny dot, and it carries a negative charge. The other electron will be a tiny dot, carry a negative charge. We're trying to put those electrons onto the orbitals, and let's take a look at it. First, we put the first electron in. We use those arrows to indicate it's spinning in certain directions. It's no problem. That orbital is empty. It can go in there. But how about we put the second electrons? It's trying to get in now. Oops, and that's some misspelling. That's coming back. Tries to get in. So what would be the interaction between this electron, first electron, and the second electron? And as you know before, this is a same charge, it's all negatively charged. The interaction between those on the electron level will be repulsion. Okay? And this, it will be repulsion. So just looking at on the charge alone, we cannot introduce the second electron. However, later on I'm going to learn in the physics, when those electrons, when the charged particles are moving around, they actually generates, they're moving very fast. They're moving fast, they actually generates, when they're moving fast, they actually generates an magnetic field. Okay, so then it actually generates a magnetic field. You can represent it by a magnet. This is the north end, this is the south end. So this is for one electron, okay? And the other electron, if it can move in the opposite direction, so if it can move in the opposite direction, it actually can spin in the opposite direction, it actually can generate a magnet like this, okay? But this one has to be opposite. Okay, so this is going to be very strong magnetic attraction. Okay, this strong magnetic attraction can actually overcome the repulsion between the charges and put the second electron onto the same orbital. But as the arrow indicated, it has to be spinning in the opposite direction. I have to spinning in the opposite direction. So, and we say, all right, let's say we got an orbital now, and we can actually put in 2 electrons on it with the opposite spin directions to use the magnetic attraction forces to overcome the electric charge repulsion. How about this third electron? Can we put third electron in? And now we're going to encounter some problems, because what is holding those 2 electrons together essentially is the magnetic forces north-south, south-north, holding the first 2 electrons, holding the first 2 electrons together. But if the third electron comes in, doesn't matter which orientation it has, you have north-south or south-north, is going to be in repulsion magnetically with one of the previous 2 electrons. So this is the primary reason why the third electrons are not, the third electrons is not allowed. Okay? So in a very pictorial simplistic way, you can have, this is called Pauli Exclusion principle. Okay, it's called a Pauli Exclusion principle. It was simply says for each of the atomic orbitals, you can only have maximum 2 electrons, and they have to spin in the opposite direction. They have to spin in the opposite direction. For the reason the magnetic attraction overcomes the electric repulsion. Overcome the electric repulsion, so they can hold it together. The third one is not allowed. Then let's take a look at the practical ramification of that. As we say before, we have the sublevels, and it all depends on the L value, 0, 1, 2, 3, 4, 5, and the list goes on and on. It's a notation S, P, D, F, G, H, and the list goes on and on. And the number of orbitals, the M value is determined that will be 1 box, 1. This one will be 3 orbitals, same energy. This one will be 5, 1, 2, 3, 4. This one will be 7. The one will be 7. 1, 2, 3, 4, 5, 6. And this one will be 9. Okay? 1, 2, 3, 4, 5, 7, 8, and this one will be 11, and the list goes on and on. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As we said before, Pauli exclusion principle says each box can only hold up to 2, and they have to spin in the opposite direction. So those are the ones you have to go in like that, going like that, going like that, and you got the idea. You got the idea. So once this the maximum number electrons it can be held on those particular sublevels. There will be 2, there will be 6, there will be 10, there will be 14, there will be 18, there will be 22, and the list goes on and on. So based on that, now we know the maximum number of electrons you can get on each of those sublevels. And coupled with this model, you should have a pretty good idea of what is the maximum number of electrons can go on each principal energy level, each sublevel. So with that, conclude the Volcast on the Pauli exclusion principle. Thank you very much for your attention.